Hi there. Welcome to a video lecture for section 2.1, Vectors in a Plane. And this begins on page 101 in your OpenStax textbook. Let's begin. So let's begin by defining a vector. A vector is a quantity that has both magnitude and direction. The endpoints of the segment are called initial point and the terminal point of a vector. A vector with an initial point and terminal point that are the same are called zero vector. So it would just be a point because it starts and ends at that single point. So a vector has the initial point and the end point. And the end point, that terminal point, usually an arrow. The initial point is usually like a single dot to represent that starting point. Hence, it has magnitude and direction. Next definition, equivalent vectors. Vectors are said to be equivalent vectors if they have the same magnitude and direction. So let's see an example of a vector. This example is asking us to sketch a vector in the plane from initial point 1, 1 and terminal point 8, 5. All right, so we see the solution here. All these images are from your textbook. So we see here that we have a starting point. We start here, and we see a little dot to show us that that's where you begin, and we end at Q, which is 8, 5, and it has an arrow. Can't spell arrow. And that's a vector. Now that's a vector when we're given an initial point and a terminal point. Notice that it's written like a regular Cartesian point, a regular rectangular coordinate point. It has a comma, and a number. All right, let's talk more about vectors. Next definition, scalar multiplication. The product of k and v of a vector v and a scalar k is a vector with a magnitude that is k times the magnitude of v, and with a direction that is the same as the direction of v if k is greater than 0, and opposite direction of v if k is negative, less than 0. This is called scalar multiplication. If k equals 0 or v equals 0, then k times v is equal to 0. So whenever you see a v, it's supposed to be a bold-faced v, and that's how we write a vector. Now let's take a moment to analyze these pictures. So we first have this vector. We see an initial and ending point. If it's multiplied by a k of 2, then we see it's twice as long. If our k is 1/2, then our vector is shortened by a half from the original vector. And if we multiply it by a negative, we see that the arrow is now pointing the opposite direction. All right, moving forward. Definition, vector addition. The sum of two vectors v and w can be constructed graphically by placing the initial point w at the terminal point v. Then the vector sum v plus w is a vector with the initial point that coincided with the initial point v and has terminal point that coincides with w. This operation is known as vector addition. So what this means is if we're adding, if we have one vector, and if we're adding, continue from that vector. This is how we add vectors. We can also subtract, and that just means that it's a bit different. I'll do another example in the future. Well, I won't. For For these pictures, they're good to know how they are and what they do, but we'll see them more algebraically, and we kind of add them and subtract them as we would coordinate points. Definition: component or component form. The vector with initial point 0, 0 and terminal point x, y can be written in component form as v, x, comma, y. Now notice that now we don't have a parentheses. We now have these like sharp parentheses. That shows that we have a vector with initial point 0, 0 and an endpoint. The scalar x and y are called components of V. Rule: component form of a vector. Let V be a vector with initial point xi, and yi, and the terminal point yt, xt, yt. Then we can express V in component form as V equals xt minus xi and yt minus yi. So essentially we're subtracting 0.2, subtracting 0.1. So if this is 0.1 and that's 0.2, we're subtracting 2 minus 1. Example: express the vector v with initial point of -3, 4 and terminal point 1, 2. All right, we want this in component form. So we want a vector that starts at 0, 0 and ends at another new point. We do not know what this new point will be. So to do so, we're going to have to subtract these 2 points. So we have a starting point and an end point. Let's go ahead and subtract. So let's take our x's to find our vector. We have our x of 1 minus -3. And my y's, we have 2 minus 4. So we have 1 minus 3, that gives us 4. And 2 minus 4 gives us -2. That is our answer. That is our vector. And notice how I wrote it with those short parentheses instead of a normal parenthesis. Definition: scalar multiplication and vector addition. Let V equal x1, y1 and w equal x2, y2 be vectors, and let k be scalar. Scalar multiplication allows us to take some constant and multiply it to both the x and the y coordinate points of each vector. We can also add vectors with vector addition, but we have to add them accordingly. So we have to add our x's together and our y's together. Lastly, we have magnitude. If we have a vector, then I just take my x squared and my y squared. Whenever I see this, I always think of a distance formula because it's essentially the same thing, but we found the difference between those 2 points. And that's something that we would have to do if we had the distance of 2 points. So that's why we say think distance formula. Example: let V be a vector with initial point 2, 5 and terminal point 8, 13. And let W equal -2, 4. Express V in component form and find its magnitude. All right, so we have 2 vectors. We have one that's called W, and we have one that's called V. But this new vector V, it's not written in vector form, or should I say component form, meaning it starts with 0 until its endpoint. So let's begin by finding V in component form. That's A. So to do A, we're going to take our 2 points. We have an initial point and an end point. So we have 2, 5 and 8, 13. That's our starting point and our end point. Let's go ahead and subtract our x's and y's. So we have 8 minus 2 and 13 minus 5. This tells us our vector u, boldface u, is 8 minus 2, which is 6, and 13 minus 5, 8. This is our new vector u in component form. Now we need to find its magnitude. To find its magnitude, just given the formula, we're going to go ahead and square the x and the y and then take the square root. So to find the magnitude of u, we're going to take the square root of 6 squared plus 8 squared. This gives us 36 plus 64, which is the square root of 100, which is just 10. So the magnitude of u is 10. That's our second part of A. B. B is asking us to add these vectors. All right, so my two vectors are 6, 8, and W is -2, 4. I wish to add these two vectors. So if I want B plus W, I just go ahead and add our X's and our Y's accordingly. So I have 6 plus -2 and 8 plus 4. This gives us 4 and 12. And that is the vector B plus W. C, it's asking us to multiply. All right, so to multiply 3v, we're going to take our vector v and multiply a 3 into each x and y. So my vector v, we said was 6 and 8. All right, let's multiply each x and y by 3. 3 times 6 is 18, and 3 times 8 is 24. Next, we have D. All right, so for D, we have V minus 2W. So for this, we want to follow order operation. So we first need to find what is 2W. So V is 6, 8 minus 2 times W, which is -2, 4. All right, let's go ahead and multiply in that -2 into each term in our vector. So we have -2 times -2 is +4, and -2 times 4 is -8. All right, so we have 6, 8, and now I'm left to work with the vectors 4 and 8, -8. So we have 4 plus 6, we get 10, and 8 minus 8, we get 0. So our new vector is 10, 0. All right, moving forward, we have a theorem, and these are properties of vector operations. So just like our properties and addition and subtraction, we kind of have similar rules with vectors. And here are your rules. First, we have a commutative property, which means I can switch around the vectors when they're being added. Next, we have an associative property, which means if I have 3 vectors, I can group them however we'd like. If I add 0, that's an identity, additive identity property. If I add its additive inverse, we get 0, which is the additive inverse property. Next, we have associativity of scalar multiplication, which shows that I can multiply however I like with the scalar. We also have distributive property and another distributive property, and identity and zero properties, which says if I multiply by 1 to a vector, I get the vector itself back. Finding the component form of vector using trigonometry. We have found the components of a vector given its initial and terminal points. In some cases, we may only have the magnitude and direction of a vector, not its points. We can identify the horizontal and vertical components using trigonometry. So here it shows us that if I have its magnitude, if that's what's given only, I can definitely find the other measurements, the x and y coordinate of the vector, using its magnitude and its matching sine and cosine angle. So here we have an example. Find the component of a vector with a magnitude of 4 that forms the angle -45 with the x-axis. So something I forgot to mention in the beginning is whenever you're working with your Calc 3 homework, always have a unit circle handy. If you don't have one left over from your trig class or your pre-calc class, just Google one. You can find one pretty easily. All right, so I often teach trig, and something I always do is I always make you draw it out. So we want the angle -45. That's 45 degrees in the opposite direction. And remember, you always draw your 90-degree from your x-axis. You always bring a line from the x-axis. So we know it has a magnitude of 4. And magnitude is the same as your hypotenuse, right? As we see from the image. So we have a magnitude of 4. Now we're left to find what this x-axis is and what this y part of our vector is. All right, so we know what angles or what unit, what coordinate point comes with a 45-degree from the negative side. So that would be the same as 360 minus 45, and that gets us here. So we know that this is the point. Square root of 2, 2, and negative square root of 2, 2. I got this from your unit circle. So if you forgot, just bring one up. All right, so we know that point, but we want to know what the vector is. So for that, we're going to use the magnitude times sine and cosine of the angle. All right, and the reason I say this is because remember, this is your cosine, this is your cosine value, and that's your sine value at 45. So that's why I wrote this down. All right, so to find the x, we know that's going to be the magnitude times cosine of theta. All right, our magnitude is 4. So I have 4 and cosine of 45, negative 45. So that gives us 4, and cosine of negative 45 is square root of 2 over 2, which gives us 2 square root of 2. Awesome. Now to find the y part of our vector, we have our magnitude times sine of our theta. Our magnitude is 4, and I have sine of negative 45. Okay, so we have 4 times sine of negative 45, which is negative square root of 2 over 2. So we get negative 2 square root of 2. So we have this vector, which is made up of 2 square root of 2 and negative 2 square root of 2. This is our component form of a vector. So if we want to draw this vector out, it will look something like this, right? Well, I don't know. I guess I don't want to leave you thinking with that. So we would have to maybe write this in decimal form, and we can have a more precise idea of that vector. All right, next we have unit vector. A unit vector is a vector with magnitude 1. So that's important. A unit vector has a magnitude of 1. For any non-zero vector v, we can use scalar multiplication to find a vector u that has the same direction as v. To do this, we multiply the vector by a reciprocal of its magnitude. So we have u is equal to 1 divided by the magnitude of v times the vector v. The process of using scalar multiplication to find a unit vector with a given direction is called normalization. All right, so let's do an example. So let's let our vector be 1, 2. find the unit vector with the same direction as v. All right, so because we have the same direction, we won't multiply by anything. But just a quick note, if I would have asked for like negative direction, then we would multiply it by a minus, a negative sign. All right, let's do A. We're going to find the unit vector with the same direction. All right, so let's start off by finding our magnitude. Our magnitude of B is 1 squared plus 2 squared, and that gives us 1 plus 4, so that's the square root of 5. All right, well, according to our formula, which we have here, it tells us that to find the unit vector, we have to take 1 divided by the magnitude times the vector. So let's go ahead and do that. So I have 1 divided by square root of 5 times our vector, which is 1, 2. All right, so we multiply that 1 over radical 5. So we distribute that. And so we have 1 over square root of 5 and 2 over square root of 5. And I know that we would want to rationalize it, but this is okay for now. All right, let's continue with B. Find a vector W with the same direction such that V, same direction as V, such that the magnitude equals 7. All right, so we have all right, so this is kind of a weird question. Well, we have already found that a magnitude of U, which gives us a measurement of 1. So this, let me highlight it, this will be found by being the unit vector. It has a magnitude of 1. So this equals a magnitude of 1. So if we want it to equal 7, all we have to do is multiply a 7 to it. So we have 7 times our new vector of 1 over square root of 5 and 2 over square root of 5. And then we just multiply. So I have 7 over square root of 5 and 14 over square root of 5. And that is our new vector with a magnitude of 7. Next question. It is convenient to write a vector as a sum of horizontal vector and a vertical vector. Let's consider at standard unit vectors. So we have j 0, 1 and I 1, 0. By applying the properties of vectors, it is possible to express any vector in terms of I and j, what we call a linear combination. So this is how we can write it. So if we have v equals xy, we can take our x coordinate plus our y coordinate, and in return, we can write it with an I and a j. And once we move further into 3 dimensions, we'll add a k. And this is another way to show a vector. Thus, v is the sum of a horizontal vector with magnitude x and a vertical vector with magnitude y, as in the following figure. Let's do an example. Express the vector w 3, 4 in terms of standard unit vectors. All right. Did I write it incorrectly? Yes. So there's a typo, and I guess I'll fix it in your notes. but the reason there's a typo is because I want it to match your text. So this is in page 106, I'm sorry, 116, and it has a -4. So I'll fix that in your notes. Okay, first we want to write it as a standard unit vector. So that just means I want my x and my y separately. So to write it as such, we have our vector of 3, -4. So to do that, I would just have to write it as 3i, and then I have a -4. So I'll write -4 and a j. I write them kind of cursive-like because I don't want to confuse an I or a J with a 1 or a 2, or I don't know. I don't want to confuse it with any number. B. Vector U is a unit vector that forms an angle of 60 degrees with a positive x-axis. Use the standard unit vector to describe U. That should be describe. Describe U. All right, well, we have 60 degrees, right? I always like to draw it. So we have 60 degrees. We always bring down that 90 degrees so it touches that x-axis. And we know we have a unit vector, right? A unit vector. A unit vector has a measurement of 1. So, and just in case I need it, I'm going to write the value of this point from our unit circle. So that's 1, 2, and square root of 3/2. All right, we want to find the vector. Well, we know how to do this already. We know that it's a magnitude times cosine and sine, right, from our last formula. So let's go back. We saw it here. We're going to take our magnitude times sine and cosine. Sine for your y and cosine for your x. But what's cool here is we're given a unit vector. A unit vector has a magnitude of 1. So really, it's just cosine and sine. So our answer is cosine of 60 and sine of 60. Times your magnitude. Remember, our magnitude is 1. So there's no extra work to do. All right, cosine of 60 is 1/2. And sine of 60 is square root of 3/2. And so if we want it as a standard unit vector, we would just write it as 1/2 I plus square root of 3/2j. So here we have a vector, and here we have a standard unit vector. Just as we described above. All right, let's do a word problem so we can apply what we've learned. Jane's car is stuck in the mud. Lisa and Jed come along in a truck to help pull her out. They attach one end of a tow strap to the front of the car and the other end to the truck's trailer hitch. The truck starts to pull. Meanwhile, Jane and Jed get behind the car and push. The truck generalizes a horizontal force of 300 pounds on the car. Jane and Jed are pushing at a slight upward angle and generate a force of 150 pounds on the car. Find the result and force the vector sum, and give its magnitude to the nearest tenth of a pound and its direction angle from the positive x-axis. Alright, so here it tells us the truck was pulling 300, Jane and Jed are pulling 150, and it created this angle of of just 15. Alright, so first it's asking our question to find the result and force. That's just the vector sum. All right, let's go ahead and do that first part. So let's write each one as a vector. So if I'm pulling 150 pounds, that gives us, well, that would give us 150 cosine of 15 and 150 sine of 15, right? Because it's not exactly along the x or the y-axis. It has an angle we need to consider. That's our vector. For 300, this one is right across. There's no angle. So our vector for that one would be 300, comma 0. Okay, we want the sum. So we want 150 vector plus 300 vector. That gives us, we just add them. So we have 300 plus 150 cosine of 15. And the other one is 0 plus 15 sine of 15. So it's just 150 sine of 15. That's our sum, our vector sum. All right, next it wants us to find its magnitude. All right, we have a new vector. We want to find the magnitude of this vector. Let's label this vector something. Let's label it r. So let's find the magnitude of r. So we take the square root of 300 plus 150 cosine of 15 squared, all of that squared, and 150 times sine of 15 squared. All right, this is just calculator work. Make sure you have a calculator out and get the right answer. You should get 446.6. That's our magnitude. All right, lastly, it wants our direction angle. All right, to do that, we're just gonna use some regular trigonometry. So we're gonna find tangent of our opposite adjacent. So we have tangent theta of 150 of sine of 15 over 300 plus 150 cosine of 15. All right, so this gives us tangent theta, and once we work this onto a calculator, we get 0.09. So make sure you take the time to do this in your calculator. We want theta, so we apply tangent inverse. So I have tangent inverse of 0.09, which gives us something close to 5. So let's round to 5. So it's 5 degrees. So this means that the resultant force, R, has an angle of 5 degrees. Let me write this down. The resultant force, R, has an angle of 5 degrees above the horizontal angle. Because technically we have a new vector, and it's made from up of 300 plus 150 cosine 15 j and 150 sine of 15 I and j. So let me write this down. All right. So I know this question is kind of weird, but now we can see how we would use this in an application type of problem. All right, so here amongst all that work, you also have your homework. Your homework is 25 through 47, every other odd. So you're going to skip an odd in between. That's found in page 120 from your textbook. So remember, you're using a free online textbook. Um, I also wanted to warn you that this class has a lot of new terminology. So make sure you're familiar with the example we did and what we were trying to find. What does it mean to be? So I had a list I wanted us to build. So component form, what is a vector? What is a component vector? A magnitude, unit vector, standard unit vectors, and unit vectors. Um, They all kind of look the same, and the math isn't hard. I know the math is way beyond you, but it will slowly build up, and it's important to keep track of all the new terminology you're learning along the way. All right, that's it for this first section. We'll continue with the next section, 2.2.